Okay, great. Thank you everyone for coming to this in-person talk at Saturday. And this is the third lecture of Entanglement Bootstrap. Entanglement Bootstrap. And the third lecture. In the third lecture, I will switch gear to talk about some gapless recent development for gapless system. So in the previous lecture, I talked about gap state. Let me just try to brief overview of the spirit and the philosophy, and try to argue that the gapless story is some extension of the story. Well, actually, it took me some time to figure it out, and in particular, people who helped me with that was David Dingjin Lin, was a grad student in our group in around the year 2022 and 23. He wrote a paper with John McGreevy about some really nice piece of observation about when DCFG chain, a spin chain as a critical point. There's some interesting equation they try to derive, and when David showing me the draft, I was thinking, oh, this is something interesting, but I didn't immediately couldn't tell for sure that, oh, this is some version of entanglement bootstrap, but David was insisting that this is entanglement bootstrap. And later, in the because I had some interest in chiral state, we actually had a chance to collaborate on a very highly related subject. After that, I become more convinced that.
等会儿他那边没有人。
Sorry.
这里真好看。
That's a question.
Mute him.
Mute which guy? Maybe they were self-muted. Okay. Okay. Yeah. So then I am convinced that this is actually a kind of entanglement bootstrap worth developing, and we are still in a and there's a lot of connection to numerics, because if you have a 1D system on a spin chain, it's easier to do numerical than the topological order in 2-dimension and higher dimensions. And for the chiral analog, which I'm going to tell you, maybe spend 40% of the lecture. We also have some numerical data, and it's quite exciting. But the stage of this program, I would say, there's a lot of new insights, and based on some are based on numerical observation, some are based on concrete proof, and I will tell my personal version of this development. And much of the follow-up works are still undergoing in John McGreevy's group. So if you get a chance, talk to John, talk to his wonderful student David and Xiangpi. Yeah, both of them are graduating actually. So yeah, we will see where they end up with next year. Okay. All right. So for gapless state, this figure of length scale was a main figure I drew in the beginning of the first lecture, and I was saying that the Hamiltonian, suppose you have a local Hamiltonian, the length scale of each individual Hamiltonian term is small. But then if we look at the wave function, we prefer to do some cost graining. This is a cost grain. And we do cells, so each cell have enough number of qubits, and the length scale. In the case of gap system, we typically want the length scale here to be much larger than the correlation length. Then the entanglement area log holds approximately. And then once we have the area log axioms, A0, A1. In many sense, we are very lucky that we get the right axiom. We can really do the proof and understand the emergent theory, the emergence of anyons. Yeah, in 2+1D is about the emergence of anyons. And about topological order at a larger length scale. So why anyons should appear, why they should have you speak each anion has their antiparticle and how they fuse and breeding. The breeding will be the next lecture. But that's the line of progress. And this part is called entanglement bootstrap for gap state. For gap state, originally I thought, okay, the for gap state, it's the progress was already made in the 1980s, so like conformal bootstrap, right? So we have conformal symmetry, and then the rational, well, like in the case of rational conformal field theory, have a primary state, primary field, and how they fuse and breed follows from conformal symmetry, and in particular have real serial algebra. So I thought that that was a sort of understood, and entanglement bootstrap with a complementary size. Oh, we're doing the gapped version of some bootstrap that people have thought about, but in fact there are new insights. I hope to tell you about that today. And here is a remark on the next scale. So it's like we have a lattice model. Yeah. Remarks on fixed point. So from the viewpoint of the fixed point, a gapped ground state should be a very stable fixed point. No matter what local perturbation you add to the Hamiltonian, the ground state will change, but the universal features will be the same. So it's a very stable. Stable fixed point. So for gap case, we'll talk about 1 plus 1D to be concrete. Like if you have an E-thing spin chain, you tune to the critical point, then you can add terms to the Hamiltonian so that the state will become gapped. So the fixed point is unstable in some sense. But interestingly, there are also stable gapless fixed point. Surprisingly, stable gapless fixed point. Fixed point. But such fixed point, fixed points do not exist in 1 plus 1D, but instead, it's like this. So think about this picture. So you have a 1 plus 1D, so 1D CFT, right? So you have left movers and right movers. They have the same contribution to the central charge. They have the same number of low-lying degree of freedom. But if since we learned about topological order, you may or may not be familiar with chiral topological order, but the idea is that think about some system that can dimension reduction to 1D conformal field theory. You can gap the bulk. So the bulk is gapped. And chiral. Yeah. If you are lucky, you can find a system such that the left movers and right movers are get split to two edges. So at the upper edge only have left movers, right? And the lower edge only have right movers. And if you do a dimension reduction to treat this strip, suppose it has finite width, you squash it down to 1D. Then the 1D, you get a 1D system with both left movers and right movers. It turns out this edge is people believe it is described by some chiral version of yeah. But this terminology is ambiguous. So it's hard to find the precise meaning of that. But that's something people get very interested in for very physical reasons. And this one, as I will argue, this should be a stable fixed point. So today, my goal is to understand some physics of the gap-based fixed point, including the unstable ones and the stable ones. Unstable ones on the spin chain and some more stable ones on the 2D, the edge of the 2D topological order from the perspective of the entanglement. So the wave function try to guess the right starting point. Yeah, so I will argue that A0 and A1 will no longer be the good choice, and we need to try harder. And in some sense, this is still an ongoing program, and we have maybe the highest density of open questions, among entanglement bootstraps. Okay. So in order to make progress, let me make some definitions. The quantum information tools, we want to extend our toolbox. There's something I haven't had the chance to tell you in previous lectures, but now I need to first remind you that there's something called the conditional neutral information, like A and C, AC and B are three systems. And you have a linear combination of entropies. So the entropies are and something minus P is the entanglement entropy or the von Neumann entropy. And if you do this linear combination, this thing is called strong subjectivity, called conditional mutual information. And the fact that this is always greater or equal to 0 for any tripartite state is a strong subjectivity denoted by SSA. And the one on the second line is delta. Delta also depends on three subsystems B, C, and D. It's another linear combination. It also has 4 terms. But don't. We need to distinguish them. It's not so hard to tell the difference. Like a delta, for delta, you have the 2 regions with the plus sign and the more volume than the terms with the minus sign. And in fact, they are the same thing if you have pure state side A, B, C, D. So on a pure state, let me write. Yeah. Suppose you have a pure state set A, B, C, D. You compute I on side. You get 4 terms, right? SAB plus SBC minus SB minus SD. But now recall that the entropy of a region equal to the entropy of the complement, which is true for pure state. Pure state. Because of that, you can replace some terms. For instance, let's try to get rid of any entropy with the region A. Sorry, I guess this is the ABC. So 2 of the terms contain region A. When we say that, we flip the entropy to the complement. So the first term will be as CD because CD is the complement of A. And for the last term, we replace this by S of B. And so we get delta. Yeah, so on a pure state, they are the same. But in general, on a mixed state, well, any U, A, B, C, D, it is not hard to convince oneself that strong subjectivity tells you that delta is greater or equal to I. Yeah, you go to talked about this one in the tutorial. Okay, those are scalar equations. So let me say those are scalars. Now, on the other hand, there are some somewhat stronger quantities to consider. One is modular homotonium, which is the logarithm of density matrix. The K will be log rho, and the subindex is the region. All right. And with the modular homotonium or the entanglement homotonium, we can come up with the operator versions. Yeah, those are operator versions. And those are stronger than the scalar versions. So you have a hat in this, linear combination, you replace x by k. And similarly for delta hat. So you can ask, well, you know strong subjectivity imply I is greater or equal to 0, but delta is greater or equal to I, which is also greater or equal to 0. So both of them are non-negative. Then you can ask the question, is it true that I hat greater or equal to 0? And whether delta hat is greater or equal to 0? Yeah. It turns out the answer is no in this case. But the answer to this question turns out to be yes.
As in eigenvalues greater than 0? But the operator greater than 0 means?
Okay. The operator greater or equal to 0 is the statement that for any state vector, this is a greater or equal to 0. This is called the positive semi-definite.
Oh, okay.
For any other. Yeah. It turns out this is true. So this is a nice result, and it's surprisingly recent. Done by Dingjing, David, as a team, and I think this should be pronounced as C. Okay. All right. So why am I telling you about the operator version? It's related to some idea of treating the computing. Look at the structure of the entanglement homotonium and ask the question whether some modular homotonium or entanglement homotonium of a region, whether it's local or not. I'll get there in a minute. Before that, I'd like to comment on quantum Markov state. And here the gives state for later purposes. This thing in the code and gives state. Well, let's normalize it by something. All right. So for quantum Markov state. As a reminder, is a hypertext state such that the condition of meta information vanishes. The simple facts are the following. So it turns out for the quantum Markov state, the I hat will be 0. Height of a rotation will be 0. But this one may not. But AC and D equal to 0, and usually does not imply delta height is 0. That does not. Usually it's not true. All right. So now back to physics. erase this part. And gap. Yeah, okay, let me start with the most boring case. Say the 1D gap is a fixed point. I said the main content of the lecture will be for gapless fixed point, but for 1D, yeah, let me first talk about the gap fixed point. I didn't talk about this because this is somewhat trivial, but now I want to use it to motivate something. So consider a spin system on a 1D chain. Imagine you have many qubits here. You have a tensor product here with space. You get a local gap Hamiltonian. You look at the ground state, and we will expect some 1D version of axiom A0 and A1 to be true. Let's see. A0 and A1. Yeah, what are they? There are some conditions on like a 1 size the interval called A, B, and C. Then you have the first condition A0 will be SB plus SABC minus SABC, the region C is 0. And 1D version of that simply 1. By the way, is this a rectangle too small?
Oh,
Is this okay?
can you see? Let me take a look at top.
It is somewhat small, but I could maybe
Still make it out. Maybe try to write it
Yeah.
bigger still.
Yeah,
Or-
okay. Yeah, only those two lines will be
Okay.
small. Okay. So the A1 is SBB plus SBC minus SB minus SD is 0. And with these two conditions, you can easily verify that. If you take this interval from here to there, this one contains several sides. In the Markov state, so the partition, in any partition A, B, and C, yeah, you can derive from the axiom that I, B, C, and D will be 0 for this partition. And from there, not only can we conclude that the linear combination of entropy is 0, we can also use this fact. It's very remarkable fact about quantum Markov state. Yeah, use this one to show that the density matrix on ABC, well, we need to take a log. After taking the log, minus log, you get the entanglement Hamiltonian. Exactly, KB is ABC minus KB. Okay, to be completely rigorous, here I assume rho is quantity. Yeah, so you have no 0 eigenvalues. Otherwise, the statement is true on the support of rho. But that's a detail. Let's not go into that too much. So once we have this Markov state, we can decompose the density matrix. That's a nice idea in the sense that you may have a very long interval, and you take a log of the density matrix. This operator is supported on some pretty large region, and you want to ask whether you can chop this into small parts. The question you ask will be, is the modular Hamiltonian local? But if you can write the big operator into a sum of small operator, which is supported on geometrical local region, then you see this operator is local. So that's the locality of of entanglement Hamiltonian. And with this, if you have more partitions, then we call this A1, A2, and AN. The K of A1 to AN will be the sum of two-side terms minus one-side terms. But I need to specify the location of the term. The two sides could be here, here, and so on. And the second term, the one-side terms, will only come from the interior side. The two sides at the endpoint are not included.
Sorry, just to make sure. So, for the definition of quantum Markov state, it is so is this mutual conditional information holds for any tripartition A, B, C, or
Good. By a quantum Markov state, we have to specify the partition. So we will see for this tripartition of the state is Markov.
okay.
But for this one, I specified ABC. But for this one, you have many choices. And we will see what the accurate way to say it is that from the left and the right condition on the middle is 0. Yeah. And from there, you can get right.
So it's not just the property of the state; it's actually related to your partition.
Yeah, it's related to the partition.
I see.
So you get a local Hamiltonian.
Well, but suppose if we glue the boundary of A1 and AN together to form a ring, then
Okay.
this seems like there is a lack of how do I say it? The translation invariance to this formula.
Currently, I haven't really assumed translation symmetry.
Okay.
I assume two entropy conditions. Yeah. Yeah. And considering a ring is interesting as well. So I was talking about the line segment, but if you have a ring and partition this into pieces, you will ask, how about, can we write the modular Hamiltonian in terms of pieces? But in that case, actually, that's an interesting example that illustrates the resultative dimension here. So it's like for the positive decision matrix, this is true. So Markov implies the operator version of Markov. But if on the entire circle, suppose you have a pure state, then you have it has a lot of 0 eigenvalues because the entire Hilbert space is large. But this is the rank 1 decision matrix. You have a lot of 0 eigenvalues, so it's actually not equal to the sum of two side terms minus one side terms. Yeah, but the vector version will be true. So two sides minus one side. Everything on the side will be 0. Yeah, this is the vector version. Yeah. Okay. So
Sorry, why does it not equal to the exponentiation of? Or why do you use a side is not equal to? Wouldn't that be the exponentiation of the modular Hamiltonian?
Good. So psi is an exponent. Well, so yeah, this part we should take care of. Yeah, that's a comment.
Okay.
Yeah. So it's like only when you have a full rank decision matrix, this is a operator equality. Otherwise, the vector version is safer.
full rank meaning some are that if it is not all entangled.
So it's the difference between this positive semi-definite and positive definite. Positive definite means the operator has no zero
Right,
eigenvalues.
right, yes.
Yeah. This can be a tricky condition for some maybe quite some models on the lattice. But the vector version is actually
With gauge, but like let's say those with super selection sectors, gauge theories, wouldn't there be zeros very naturally?
yeah, you're right. So when you have a super selection sectors, you have orthogonal projectors
Right,
to the
right, right.
to the vacuum sector. You know there are no other sectors, so it's
That's
have
right.
zero overlap with the state. Then you have kernel, you have zero eigenvalues.
That's right. That's
Yeah.
right. Oh, then in that case, in general, this equality is
So this is a can be used in some cases, but with some cap.
I see.
So it's not like a mathematical statement, but when you first try to understand the physics and try to
Okay.
argue something, you can first try this, but maybe you encounter some difficulty, but sometimes you succeed. You find the right formula. Yeah. But the vector version is safer. So actually I also wanted to comment around here. So the vector version. I hope people can see vector version are the following. So for Markov state, given a Markov state, a quantum Markov state, well, I guess it's convenient if I purify this into some bulk partitions. Yeah, so by that I mean just IUC B is 0, delta BCD is 0. Yeah, for such a state, which purified some state Markov state on ABC, it turns out an act on psi is 0, and delta hat acting on psi is also 0. Why is this true? Well, if we look at something like this, it's like we will show that delta is related to I on the pure state. We flip the support, this K on AB, you can flip it into K on CD acting on the state. Like the vector version, the flipping property holds on the vector version, so you can easily prove that this is true, then this is true. The second line is implied by the first line.
Sorry, do you mean you assume you only work with pure states?
I purify the density matrix. So if you want, you can have the another version. I had AC condition B acting on UAB C 0. Yeah. Did you prefer this version? You have it.
Okay, so the region D is the insular resistance.
Yeah.
And is it the local equation or is it global?
In this blackboard, currently I'm talking about some general statement.
Yeah.
Without referring to the physical system. So
I see.
Yeah. To 0 if delta is 0. Yeah, the vector equations. Yeah, those are we call it the vector. Yeah, vector-like equations. Those are pretty robust. Okay. I give you something around here. I need to finish some discussion about this 1D gap state before telling you something more interesting. All right. So first, suppose we have an operator equation. One sum of the two side terms minus one side. And there will be minus one such terms and minus two such terms. Yeah. Okay. In that sense, we will say the entanglement Hamiltonian is local. It's local, then the rho A1 to An will be exponential minus A1 to An will be exponential some local Hamiltonian. Yeah, are reconstructing Hamiltonian. So it's like you have a decimal matrix on a large system. It's this one by definition. But suppose this large operator can be split into small operators. Then you have exponential minus the local Hamiltonian. Right? And this is saying that your state is like a Gibbs state of some local Hamiltonian. Right? Even if you don't have this, it's an exponential minus some Hamiltonian. It's a Gibbs state, but if it's not a local Hamiltonian, it means much less. But if you have this, it means something. But in general, this needs to be taken care of, and we will be more careful. Like ask whether it's true approximately, or maybe it's even maybe it's even worse than that. We need to be somewhat careful.
So what is REC? H
Reconstructed.
Reconstructed.
So yeah. C means reconstructed.
When you say n minus 2, do you mean you ignore the endpoints?
It's like this. So when we have A, B, and C, they say we have A, B, we have B, C, but we only have B. We only have the middle.
So it's kind of like the end point is taken out.
Yeah. So follow the Markov state structure. You
Yes.
decompose the piece by piece. Yeah, then you automatically get this equation. Right. So because the gap is well, I don't want to get to the gap is immediately, but let's make this observation. So this Hamiltonian, this reconstructed Hamiltonian, local Hamiltonian, and two side terms and one side terms, and it's actually very similar to the quantity delta. The delta BCD, the KBC, right? Delta hat. I'll review that. Delta hat. BC and D is KBC. So P minus KB minus KP. So it's like two side terms minus one side terms. And suppose you do this on a circle. Note this is somewhat dangerous, but let's do it nonetheless. So it will be a sum of deltas on delta factor on I, which means that we take the I side in the center and we take this region. So you have this term, you have that term, and minus this one and that one. Yeah, and you make all the translation of, yeah, the same thing everywhere on each side. Then you get this one. Factor maybe I'm off by factor 2 or something. Yeah, but that's a detail. Divided by 2. I think that's it. Okay. And now the funny thing is the following. You take your original state, maybe a pure state, some ground state of a local Hamiltonian, and suppose it's a gap the fixed point. And it satisfies the 1D version of A0 and A1. If so, it has Markov state, right? So for each partition, yeah, you have delta A1 is satisfied. You have delta is 0, so delta. Okay. The expectation value is 0. You have the scalar equation, but actually it implies the vector equation. So it implies delta hat acting on psi is 0. So the H reconstruction acting on psi. So this Hamiltonian is reconstructed from the state. It turns out if you use this operator acting on psi, you get 0. But we also know that delta hat a no negative eigenvalue, so delta hat on any side I is greater or equal to 0. So the 0 eigenstate. Yeah, 0 is the smallest possible eigenvector of this one. So in fact, you get a frustration-free Hamiltonian. Am I right?
Why frustration-free? Because there is translation invariance.
No, frustration-free means. Oh, sorry. I probably use the wrong term. I think frustration-free means you first you have projectors, then you take the minimal eigenvalue for that projector. But here we have a set sum of operators. Each one takes the smallest eigenvalue because the height on I acting on C is 0 for any I. So each Hamiltonian term takes an eigenvalue which is the smallest eigenvalue. Maybe I shouldn't call it a commuting a frustration-free Hamiltonian because those are not projector. But you get that idea. I think the following is true. Yeah, let me correct my statement. I'm saying because of this and that, we can derive that psi is a ground state. It is a ground state. Of H reconstruction. Yeah.
Oh, okay. Okay, but then it means that this is a ground state where all the delta I also commute.
Do I know that?
Because all the delta I acting on psi is 0. But okay, this is they still may not commute because it is just one vector. Just all the commutator acting on psi is also 0.
Yeah, maybe you are right. So I need to think more. But yeah, let's write down this question and then continue. Good. Right. All right. So yeah, made a story about gap the fixed point in one dimension and related to the give state and that the ground state is somehow So the reconstructed Hamiltonian has the original state has a ground state. That's pretty interesting. But now let's ask a question. Let me ask a question to motivate.
The fact you said that psi we have made use of A0 and A1 as in that ensures that delta I acting on psi is 0. That is where we use A0 and A1.
Yeah, A0 and A1. So A0 and A1 It's a
that the state is a
insufficient.
Markov state.
It's not enough to draw this equation, but the argument somehow requires this. So we better have that. Okay. Yeah. It's some funny situation that I couldn't.
And here it is one-dimensional because we can think of this as a chain.
Yeah, it's a chain.
Did you make these statements for two-dimensional gap space to a reconstructed local Hamiltonian for two-dimensional?
Yeah, that's an excellent point. Actually, we did that. We did that in the modular commutator. The paper we tried to understand the chiral central charge and came up with the formula. Yeah, maybe let me make a brief comment. And then I'll say something about the formal 1D fixed point. To be reconstructed Hamiltonian. For disk, so you have a state on the disk, and suppose the disk is large enough. And then this large, and let's fill in the large disk with hexagons. Imagine you have a hexagon lattice filled in the disk, and then you can take a look. So this case is minus log. And for the 2D work, we have axioms A0 and A1 on each of the cell, smallest cell on the cross-grained lattice. The smallest cells are on a 7 hexagon size. You have those A0 and A1, and those conditions imply a Markov state condition in C, B, and A. C, B is 0. And we can argue from that I fact AC from B is 0 as well. But we need to be careful. This may fail.
IACB, there is a little square at the corner.
Yeah.
IACB equals 0, you draw a little square.
No, this is something.
Good.
Thank you. Okay, it turns out we can decompose this one into local pieces. The local decomposition will be sum of A on 3 sides minus the 2 sides plus that's for 1 side. But we need to take care like which 2 sides are allowed. So some near the boundary are not chosen. Yeah, we need to remove some of the 2 side terms. If the 2 are both are on the entanglement boundary, we don't have that term. And all of the 1 side terms are from interior. The side has the interior of the disk. Yeah, but that's it. It's like we have a local decomposition. We can argue with some term. We could be wrong sometimes. But with that, the same philosophy, you can argue that this is the state is a thermal state, if state of some local Hamiltonian, and so on. If you assume that it's not very far away from our argument of the chiral central charge, the formula, the modular commutator formula. Maybe I should write some history. Modular commutator. Sorry.
And for pure state, we have a state which is simultaneously pure and thermal, which means the other eigenvalues of the Hamiltonian must be all infinity.
Say it again.
in the pure state case,
Yeah.
we have psi, which is simultaneously the ground state and the thermal state of the Hamiltonian, right?
Okay, yeah.
Which implies all eigenvalues except
Yeah.
one of the Hamiltonian are infinity.
Yeah, so that's an example that this approach fails. It's wrong. Yeah, so
Sorry, I didn't get your point. Sorry.
So in the right half of the blackboard, first we derive the reference state rho, the thermal state of the reconstructed Hamiltonian.
Mm-hmm.
And when the reference state psi, the pure state, we also derive it is the ground state of the Hamiltonian.
Uh-huh.
So it is simultaneously an eigenstate and a thermal state, which implies the Hamiltonian must be somewhat strange.
Oh, you're right.
yeah, so that's why I'm saying this is a very attractive idea. Sometimes it give us some nice insight, which turns out to be extremely useful. But this is at this stage not mathematically rigorous, and you can come up with very extreme counterexamples, and that one is one of them.
But have you tried to check this Hamiltonian as well, let's say numerically, and see what happens? You have checked it?
Yeah. Actually, this is a problem we always want to check, but we get busy at a different stage. But I think in the recent paper by Xiang Li, David Lin, John McGreevy, and one other author about, I think it's called chiral gap state are universally non-topological or something. That one. And in one of the appendix they check this, and it seemed to work.
I see. The thing is, if you started off with a disk, then something wrong can happen at the boundary. But then you just pretend that you can do a translation invariant thing and complete it. Then maybe it leads to some sensible Hamiltonian.
Yeah. It turned out I would say it worked. Yeah,
Okay,
but theoretically, why this works is still mysterious. Because this data hat at the Hamiltonian term,
Mm-hmm.
it seems okay because it's non-active, right?
Right.
It's bounded from below.
Right.
But actually, it sometimes get infinitely large eigenvalues. It's not easily to be bounded in any way.
Yes, but in the actual examples that he constructs, these are just it's just like Pauli matrices locally. Then I don't think there can be any problem.
Right.
It's just a local term.
Yeah.
So it looks like any normal Hamiltonian on the spin chain, and so that it works. But I don't think in those cases there can be these problems because they're just Pauli matrix.
I agree with you. All right. Now let me continue with our 1D. So take this figure and those equations. Continue from here. So here I was talking about the gap. And gap Hamiltonian. Let's start from this equation already. We assume the A0 and A1, and even that's not quite enough. But let's try something crazy. Although this one is not completely grounded, let's try to try this on something else. To try this on a 1D CFT ground state. Ground state CFT vacuum. It's a ground state of some your favorite spin chain Hamiltonian as a critical point. You get your state. CFT. And try to write. Let's try to do it without getting the principle on this stage. This is a bad way to motivate, but nonetheless, I want to do that. Still do two sides minus one side. Yes, suppose the state is on a circle. The state circle. And okay, let's claim this will be called the reconstructed Hamiltonian. As what David and John call it, the reconstructed Hamiltonian. And well, again, this is the sum of delta. divided by 2. And as an operator is greater or equal to 0. Right. Now guess what? So is reconstructed. Let's try to at the state. Well, this thing is reconstructed from this decision matrix, the ground state. At this Hamiltonian back to the original state. What do we get? In a gap state. So this, let's call it a gap. You get 0 on the right hand side. But here, well, of course, we cannot get negative value. It should be something either 0 or positive. So what do you think? It turns out it's proportional to the central charge. L3, L2, L2, times the number of sides. Number of sides. Yeah.
Oh, sorry, that's a vector you get? There should be a vector.
Yeah, it should be a vector. So it's proportional to the state. Times the state. Yeah, so the next thing is that central charge comes out. Yeah. Yeah, this should might sound surprising, maybe not surprising, but well, I will argue in a minute why this is a bad way of modeling this equation. But I want to first show you the equation. Where does the log 2 come from? The log 2 come from the fact that you have two sides, right? Two sides, k on two sides minus k on one side. And you take the expectation value. You have log. The CFT entropy is proportional to the log of the next, the log 2 times of length L minus log 1 times L. So this one minus that one is log 2. So proportional to, or is equal to 2 times divided by 3 log 2. Yeah, anyway, so you get that here. Let me say why this is a better way of deriving this formula. So for the gap state, because we have A0 and A1, general Markov state condition, we actually did not assume any translation symmetry or anything. Even if the partition here, we didn't take the equal size, you combine 2 of the sides, there's no problem. You can call this combination combined one as the 1, 1, 3. The third one, size is large, is okay. We always get the same form of the equation. But here, when I wrote k2 minus k1, 2 sides minus 1 side, we really had to assume some distance, some sense of distance, because the CFTs are conformal. Yeah, it's sensitive to geometry. It's not a topological quantum field theory. So if we change the size of the cells, it will not look like that. Yeah.
But isn't it expected, because we expect something like the distance or length scale to emerge from a CFT. So if we have chosen the wrong distance or wrong length scale, it should not look like a CFT.
Right. But what's the wrong length scale? The wrong length scale would be some length scale that's too small.
No, I don't mean the global length scale. I mean if we have randomly merge some sides into one side, then the system will look very strange, because the length scale is not uniform throughout the system.
Yes and no. Yes, because distance is important.
Yeah.
And no, because on CFT you can have the distance in the individual lengths of an interval is not preserved. The cross ratios are preserved. Actually, I'm going to talk about cross ratio next. Yeah. So the contrast would be the following. So this idea of the reconstructive Hamiltonian, this for the gap state in gap. The result is topological, and CFT is geometrical. And if we get the same equation,
Here in the gap, I need to just one clarification. In the case of the CFT, so what we have given up is both A0 and A1 and replace it by what have we given up and what have we adopted?
yeah, so certainly we give up A0 and A1. But it's an extremely good question on what's the replacement. And that's what I'm going to tell you.
Okay, so you first of all that is this notion of the quantum Markov states, and so you derive this reconstruction for gapped phase that is expected to annihilate the wave function. Now for CFT we have given up A0 and A1, so it is not expected to be 0, and you first check what it gives in an explicit CFT, and that is what you get. Can I say that at this level it is a check, an observation that if I apply it on a CFT, then this is what you get. Can I say that?
That's not a UN check. It's just my like I just came up with this way of explaining this morning, to be honest. And this is not in the paper by David and John.
I see.
Yeah, but the formula is there. So in fact, this is a formula they keep using all the times. I first give a really bad argument, but then I'll tell you the better one.
Okay. But when you say the modular commutator, that is the fact that J equals pi over 3c minus, that is a result from CFT.
No, there is a CFT argument, but we don't want that.
Okay.
Because we compute this from the bulk, and on the bulk we have a approximate Markov state. We have A0 and A1. We want to understand why this is true based on area law. We are still making progress on that.
But when you wrote this down, modular commutator, why did you write that down there? I also
because someone asked some questions, and wanted to answer the question, but somehow.
Okay. I clearly have missed that point, but it's okay. I'll watch the video later.
Okay. Yeah. So if you believe me, we already get some result. If we say the central charge is greater than 0, maybe it sounds boring, but it's
you
not.
said this is a result because it
delta
is positive definite.
Yes, delta is a positive definite. Yeah, delta is greater than equal to 0.
Okay, sorry. Because you say it is not 0, therefore it is some number, and now at the moment you're calling that number C over 3 log 2 at the moment. But it is not, therefore you say this is not a check of anything. It's just that I would call this eigenvalue C. But then whatever this C is, whether it is central charge, whatever, it is greater than 0 because delta is positive definite. Okay, now I get the logic.
Good. Yeah. Right. So by the way, so this maybe let me say one last thing before you read. So this ground state, the argument about the ground state is less than hand waving is some really bad. If I want to somehow start writing down the equation, but let me say that even though this equality is not true, so it requires some care, even for the gap fixed point, and the formula, the reconstructed Hamiltonian for a critical point, the gap is fixed point. Turns out it works surprisingly well in some sense. It's like you can use this reconstructed Hamiltonian, diagonalize it, and find all the low-lying state, not only the ground state. So let's say the eigenvalues, eigenstate. eigenvalues. So the first one is somewhere, and the second one is somewhere, and so on. So if you take the Ising chain, yeah, in terms of the first few eigen, yeah, the energies are correct ones. So yeah, it's pretty nice. In reality, the works nice, and when we have a longer and longer spin chain, the reconstruction appear to improve. So yeah, I guess we should try to understand that.
Yeah, basically this means the scaling dimensions are encoded in the ground state.
Yeah, indeed. So all the scaling dimensions are encoded in the ground state, and the conformal symmetries should be encoded in ground state. Even the Virasoro algebra, the entire Virasoro algebra should be approximately there.
Yeah, but in the other hand, I guess there should be a better way of extracting the scaling dimensions other than constructing.
I also believe that, and we are still thinking about that. All right. So what I'm going to say next? Okay. Now now I'm going to start answering Jenny's question. What's the replacement of A0 and A1?
Sorry, there's still one extra gap. In the case of CFT, it is not because we have given up A0 and A1, so H reconstructed does not annihilate size CFT. But why should size CFT be an eigenstate?
Yeah, I haven't answered this question. It will come after this part. And since I haven't erased it, the better that the current one. This number times the stick. So 1D CFT. Excellent. Yeah, what do we know? Right. So it turns out the modular Hamiltonian, the fact that the modular Hamiltonian is local is better known in CFT than in topological field theory. In topological field theory literature, we don't find the equation wrote is a modular Hamiltonian. Basically, the sum of local terms. Yeah, that's why we further the jump using A0 and A1 and some argument. But for CFT, the result is a better known, so it's a single interval. Single interval. Let's see, X1, X2. It turns out the show X1, X2, and take a log minus log. It is proportional to what? Some integration of x. A function of x. A square negative tensor. I think there should be some constant. The constant would be the entropy entry. And the function, what is the function? The function is like this. In some quadratic function, it is super well known. Probably there's some proportional factor. That
Is this row x1, x2 density matrix from a CFT vacuum?
is this from the CFT vacuum?
Oh, okay.
Yeah.
I see.
Yeah, the answer is yes. Yeah. The entropy from x1 to x2 is divided by 3 divided. Epsilon is some cutoff. Yeah, from the single interval entropy, single interval entanglement homotonic. This so is an operator equation. I guess we can recall it again. This operator from CFT, you know, it's the right hand side. The right hand side is a quadratic function times Rex energy tensor integrated over this interval, 1 plus something. And this piece is the logarithmic entropy of the CFT ground state. Yeah, so it's an operator equation. And suppose we apply CFT to the quantum spin system, the manifold system, 1D fixed point, 1D ground state. Lattice. It turns out there's some vector equation we can choose. There, the originally argued by Bowen, Jing with that. Let's try to make this stress energy tensor part vanish. So we came up with some combination of single interval. So if you have 1, 2, 3, 4 endpoints, you can come up with those. So if you take this interval type ABC, AB, then you get this function, quadratic function. On BC, you get another quadratic function. And you have some other choice, A, B, and C, you get some quadratic function. And you have everything. And got another. So 1, 2, 3, 6. All of them. Yeah, so right. Okay, it turns out there is a unique combination to make the to make the stress energy tensor vanish after scaling. And for defining that, I had better introduce the cross ratio. Let me write the cross ratio here. Cross ratio. Cross ratio is super important in conformal field theory. It's a ratio of distance that's an invariant and a global conformal transformation. And the eta determined by 3 intervals will be A, the length of A, length of C, divided by the length of AB, and the length of BC. Hope this can be seen. A, C, A, B, and BC. Okay. So the cross ratio is between 0 and 1. It's from 0 to 1. So I don't want this to be 0 and 1. The moment that we are from 0 to 1, the open interval. Okay. Let me define. So the solution and David came up with what was this. So and we call it K of D. Actually, that's not the reason, but he was calling it as K of delta. But I thought delta was defined, so I changed it to D. Okay. H of eta, where and right, so the operator is this one, and this function is the so-called binary entropy function with the eta log eta times 1 minus eta log 1 minus eta. Yeah, so actually from the CFT argument, you get an operator equation instead of a vector equation. So the operator version is a simply operator version. And K of D is C3 H of eta. Right. So far so good. Is the notation clear? All right. So you see the K of D is a linear combination of some delta and some I. And as I said, delta.
So what do you mean by operator version K equals?
So this is the vector version. This is the vector. Okay.
This
But H is a number, so I got confused.
H is this times identity simply.
Oh, it's an identity operator.
Yeah.
But if it is an identity operator, then there would be lots of ground states.
Right. So this is not the reconstructed homotonic.
Oh, okay.
Yeah. Yeah, we're getting there. So first, I was trying to answer or partially answer your question on what axiom do we have.
Okay.
We will say, I would say this is the one axiom, but later we will see some maybe even more compactified version. Or maybe you will see very soon. But this is a correspond to some axiom, so something we want to assume some condition without assuming the full CFT structure. And this one is some nice things because, well, if we look back to the axiom A0 and A1, it's some linear combination of entropy gives you 0. So it's some structureless quantity, right? It didn't tell you what values gamma, the subleading term gamma of the area law is, but nonetheless you can derive the quantization of gamma. That's very powerful. We want to make similar progress then with better assume some structureless things.
This combination, the definition of K, was it designed initially to the original motivation was it to remove this first term in rho x one, this fxtx term, or
Remove this term, yeah.
so the original motivation when you came up with this is to remove that term.
Yeah, but for David, yeah, I think his original motivation was to remove that term. But there are other ways to argue.
True, after you remove that, then the linear combination of operator, it will equals to sx1 ixj.
Yeah.
Then it becomes a number like object, it's
Yeah.
identity.
Yeah, each one is some number times an identity. Only these terms are collected here.
I see.
Yeah.
Sorry, I have a question about the operation version.
Yeah.
For example, if we start with the critical icing chain, we have the 2 bits on each side.
Yeah.
And we can add some unused degrees of freedom. For example, we can make each side a 4-dimensional space, and we only use the first 2 dimensions.
Right.
Then the state is in some sense the same, but the operator equation should not hold in the new case.
I think I know what you mean. It's like on the unused qubit, you have some divergent part in the
Yeah.
entanglement Hamiltonian.
Yeah,
Yeah.
it should be completely unrelated. to
Right.
the stuff.
Yeah, I agree.
So it should need some modification.
Yeah, I guess so. Yeah, but somehow on the reasonable spin chain, this could be tested. But actually, we do see some large errors for the operator equations. But for the vector equation, it turns out the numeric is much better. Let me first talk about numerical test. Then I will write down another version. Yeah, maybe first I'll tell you some numerical tests, and then I'll tell you the argument of the reconstructed Hamiltonian based on this philosophy. And then I talk about some even more compact version of the axiom, improving from those ideas. Okay, so numerical test. So we divide the circle. So take a CFT, one of your favorite CFT, maybe the Eaton CFT. Circle partition into A, B, C, and D. And we cut this in a symmetrical way, such that the cross ratio can be computed easily. The cross ratio goes down to be C will be a half. So why is this a half? It's because the AB you have next to it. Let's assume the radius is 1, so you have 2. The length of BC is 2. The length of I messed up. Sorry. On the numerator you have A, the length of A and C. The length of A and C are square root of 2. The square root of 2 times square root of 2 divided by 2 times 2 is So the vector equation, we consider the angle of vector equation. We find like square expectation minus the expectation minus square, and take a square root. Now we can draw a figure like the angle of the yeah, with the number of sides. Yeah, you can have n, let's say n of A, the number of sides in A. And you have 1 side in A, 2 sides in A, 3 and 4 and so on. And the error decays. I don't remember the data, but that's the kind of test that people are doing. And I guess for the Eaton chain, you can do it on some sense, but maybe the test is better on free formula. I believe that.
So you mean it is approaching it is indeed approaching the identity operator.
Yeah, so it goes to 0. Yeah, it goes to 0 at large n. Large n.
So it means that generically, if I have work on very small scales, then K is not yet an identity. I have to take some thermodynamic limit before it begins to look like an identity operator. That I guess makes sense. Because at least the construction of this relation for KD, the definition, turns into a constant if we have a CFT.
Yeah, that's the idea.
So certainly you need something bigger to make it into. Okay, I see.
Yeah. All right. So now I'd like to give you a better argument of this one. All right. So the philosophy is again based on the idea of canceling out the quadratic contribution of the operator part. So suppose you draw a curve. You have equally spacing intervals. And you have the two side terms. And minus the one side terms. With the red coefficient. Yeah, it turns out this thing gives you a constant. Well, that's right. Actually, I guess it's 0. So it gives you 0. So the operator part will be cancelled completely. Yeah, that's one way to argue this. But this rely on this geometrical argument, and you need equally spacing the intervals in order to have two side term minus one side term. Otherwise, the coefficient will be more interesting, depending on the cross ratio and so on. And I should comment that based on this idea, there's a CFT search program pursued by John McGreevy student in particular David and Xiang Li. Yeah, they were trying to figure out the constraint on the wave function. So it can be searched from four-side systems. In principle, we want to do larger and larger system, but to start, we can use four-side with some finite dimensional Hilbert space, 2-dimension. David originally did the 2-dimensional one, but they search Q-trade and so on. It's like you can try to identify some state, and then impose the condition, impose some axioms. And so you exclude most of the state, but you're left with a few good ones. And they argue those are candidate of the CFT wave functions, and the reconstructive Hamiltonian are candidate of fixed point CFT Hamiltonians. Yeah, so that's some numerical approach, I think. And some people, including Janet and their work is interesting.
Yeah, I tested it. It's very, very good. We tested, yes.
Oh yeah, tell me more.
Examination, yes.
I see. Okay, good. So far this is for 1D. Now I'm going to start motivating a related problem in 2 dimensions. And why I find this fascinating, and by studying that problem, I believe we are about to find some refined version, some even better version of the axioms on the fixed point. And there's also the story about chirality, why the chiral state should have a boundary that's gapless and may become most likely a conformal boundary. Oh, I see. So I have 20 minutes left. So I went a bit slower than I thought, but I think I could cover.
You know, if we have booked way more classrooms on the weekend than we need, if you need more time, you can do it also tomorrow morning.
Yeah.
But I'm glad you talked about it so clearly, so I think this is worth it.
Okay. Here. The chiral see. Yeah, as I motivated briefly previously that this 1D system, if you are lucky, you find a 2D system, which looks like it after the rate reduction. Let's see, chiral with some gameplay side. But this should be very mysterious. But let me give you an example. So we all like eating model, right? So eating CFT. I have primaries, vacuum, sigma, and psi, right? That's one of the simplest rational CFT, the minimal model. And here you have easing anion theory. Three anions, one sigma and psi. And it's chiral one. Why is it chiral? So you can look at the set of topological spins of the anions. Will be one to identity, the vacuum is the boson, and sigma is one beta. So if you look at the spin of the particle, it's not the same under it changes under time reversal. So under time reversal, this should be e to the minus 10 over 8. Yeah. And because of that, and suppose you you compute the chiral central charge, it's non-zero. All right. Right. So now that we have some idea on the 1D fixed point, and this 2D system, the dimension reduction to the 1D system, and suppose we believe that, then we would try to look for the similar equations on the 2 dimensions. It's like we have 4 points. So what will become 1, 2, 3, 4 for different line segments in the 2 dimensions. But this condition, the vector fixed point equation can be assigned proportional to size. There is some local, imposed on local regions. So we don't want a condition that touches both the upper edge and the lower edge. We want some more local ones. Motivated by that, we can consider regions like that. Yeah, this type of region. And some regions have the boundary like this one. Right. So you also have 1, 2, 3, 4 for different points. But it turns out this is not quite enough. In the sense that if we compute I, A, C, and B, it's okay. Well, it could be independent of the shapes that goes into the bulk. So if you try to define the region, it's okay. You depend on some function of the endpoints. Yeah, that depend on the 4 endpoints. And but delta is not good ones. So because here we have I and delta, that's why I'm talking about I and delta. Depend on the bulk. Yeah, what do we miss? So it turns out we missed the fact that we can have another completion of the regions into the bulk. We can have a region that looks like this. A prime, C prime, B. It turns out if you compute I on A prime, C prime, B is not good. So depend on the block. Yeah, but depending on the block, I mean, if I change the shape
Oh,
locally, then the value changes. We don't want that. Yeah, it's something that depends on the endpoint.
Right. So in this kind of computation, you always need a reference state, right?
Yeah.
But is there a like computable reference state for carry for the border?
That's a good question. Oh, I don't know exactly solvable models, but there are analytical wave functions. You can find in literature built from CFT correlators to put some qubit in 2 dimension, and it's a spin model.
I see.
And another class would be a P plus IP superconductor and transinsulator. Those are free-forming systems. They could be chiral, but no anions. It's harder to simultaneously have chiral, non-zero chiral central charge and anions. Those models are usually hard to simulate
usually infinite dimensions.
in infinite
I
dimensions.
think we have Killer honeycomb, which is
Yeah.
basically the gating of the P plus IP model. But I'm not
Yeah.
sure how difficult it is to numerate this time.
It's somewhat difficult, but people can still try to make progress.
Yeah, because basically it's analyzing the fermions coupled to each field.
Uh-huh.
Yeah. Yeah.
Yeah.
Okay. Right. So let me also state one challenge. So one challenge for chiral system is actually the following. So for the 1D system's critical point, usually we have a large class of models which are translational invariant. We know how to measure the distance. So this is link 2, this is 3, and so on. But for chiral state, suppose we, for example, we complete this thing into something in the experimental setup. So the quantum Hall state and topological order, they don't need symmetry to protect. So you can add all kinds of disorders and make the edge irregular, and you still have the same phenomenon. And it's an extremely good question whether this wiggling irregular edges are still conformal in some sense. Can we argue this is conformal? But then we run into difficulty, like we don't even know how to define the distance. Then how do we define class ratio? But it turns out the idea around here solves the problem. So like if you know I and delta, chiral irregular without knowing distance measure. Irregular. You can compute I on this region and delta on this region. With the same endpoint on the edge, yeah, you get the same endpoint. Then it turns out we can try to solve C and eta from 2 equations from I. Is it true? Okay. Oh, did I erase some line? Okay, never mind. I is C over 6 log minus eta. Delta is C over 6 log 1 over. Yeah, it turns out from this, we can really solve for 2 numbers. C and eta. Yeah, so we have cross ratios. For some quantum entanglement. Well, you may like or don't like this word of quantum cross ratio, but here what we mean is we solve this from entropy constraint without knowing the distance. We don't need to know the distance, but we solve it. Quantum cross ratio. And quantum cross ratio is this eta, and this is the central charge. Central charge candidate. So from any state, we can play with this game. We can choose the region, we can compute ion data, and then we compute two numbers that depend on the following point.
What do you say is a quantum cross ratio? Why quantum cross ratio and not cross ratio?
I would say this is a cross ratio from quantum.
Okay.
From the state.
Okay, yeah, this is.
Yeah, but now we can define the C and eta from any state. And C will be greater than 0, eta will be automatically from 0 to 1. And it looks okay, but that doesn't mean eta is a cross ratio. But then we want to derive this from somewhere.
But at this point, when we can talk about cross ratio, it sounds like we have some conformal symmetry. Is it obvious that this chiral boundary always have conformal symmetry or just gapless?
Yeah, that's actually the question that motivated me to participate in this one, and that's the most exciting part for me.
Okay. And your conclusion is that they're all conformal?
Not really, but it's under some assumption, some analog of vector fixed point equation. Under a version of the vector fixed point equation, it will be conformal. And we have another way to write the vector fixed point equation, which might be even
not conformal.
No. Okay, there are two questions. First, as a series, we can derive something like under some assumptions, we find that we can derive the conformal geometry. Then we say this is conformal. But second, we do want to test our theory. We test this for P plus FP superconductor or something else, anything that we can compute the cross ratio and check our prediction. It turns out the numeric works nicely. It's not just nicely, it surprises us. It really surprises us. Is that we put the state on some irregular shape without any fine tuning. It turns out the cross ratio. Well, I'll tell you what happened.
Okay.
It turns out the numerical, it's surprisingly accurate. So now I turn to believe that conformal geometry emerges without symmetry constraints. So it's just there for many body reason. Yeah, but we couldn't prove this.
But is there any Hamiltonian that give you gapless, but let's say Lipschitz type of theories that is not conformal but scale invariant?
That's a good question. So far we haven't found such.
Whether if I try to compute wave function, what do I get?
Yeah, that's a
There's
good question.
one-dimensional pretty Hamiltonian, which is scale invariant but not conformal, which is called the chiral clock model on paper of Stockdale solution.
And
I have a lot.
have you tested this?
No, because that model is not exactly solvable.
But
Numerically is rather difficult. We have made some attempts, but the results is not.
I'll be very curious.
Okay. Now let me continue from here. So we have a chiral edge with some 4 points. Because there are many points, you just pick one of the points And then you can compute I and delta, which depend only on the 4 point. And then from there, we can play our games and solve C and eta uniquely using those formulas. Okay, but C and eta may not be so meaningful unless we impose some conditions on the wave function. So when we take this, so I don't need to erase this equation. Is the eta is solved from here. Put eta here. Eta is here, right? It's eta. And the operators, well, this one was copied from the 1D, so now I erase it and give the 2D version. Is on this. And I is computed from this. Okay. So we impose the vector fixed point equation like this. Yeah, so it's called vector equation or vector fixed point equation. Yeah, I erase the prefactor. So remember the prefactor should be eta c divided by 3 is okay. C left plus C right divided by 6. Yeah, this thing is already taken care of by this part. So yeah, so this is true automatically. Right. But what's the difference? So it's very similar to the 1D version. The only difference is that we don't impose the class ratio by hand. We don't need to know the distance, but we solve it.
Mhm.
Yeah, it turns out from here we can derive some very nice things. The first one is that this vector fixed point equation is equivalent to another very nice looking condition because stationarity of C. So it's like saying C C is this one, so computed from the state. It depends on the state. Minus C perturb it a little bit, psi plus delta psi. One increase in the first order. Yeah, in other words, it's a delta, it's called delta C. Yeah, delta C is 0.
Oh,
It's saying some quantity, the quantity C we define from the state is stable. So if we perturb the state, you have, yeah, the deviation only come from the second order. This can remind people about some theorem in quantum field theory called the C theorem.
mhm.
And there's some logical idea of the C function, which is monotonic and the RG fluid, and which is stationary at the fixed point. And if we assume that the quantity C is stationary at least at the neighborhood of the fixed point, we can actually define the fixed point this way is equivalent to impose the vector fixed point equation
Mhm.
on the state. I find this very interesting for two reasons. So first, the vector fixed point equation has an operator, and the operator has eta, and the cross ratio has the geometry in it.
Mm.
And this one, it seems like we are talking about the C, the quantity C. So it's a kind of complementary. So one is manifestly talking about the geometry, another manifestly talk about the C, the degree of freedom, and they are sort of equivalent. And this reminds me of the action principle. If delta S is 0, and give you the equation of motion. Or maybe you can come up with a better one. Anyway, okay. Yeah, so yeah, they're equivalent, but maybe we can learn something from the other formulation. And in fact, one open problem was whether this C is really a C function. If you compute the
It's
same
monotonic.
thing in some quantum field theory, is it a monotonic under the change of length scale? That's an open question. but that's just a get started. And the second one would be my favorite.
But here, this C is the C that is extracted from the computation of delta and I.
Yeah. And numerically, we will find that this is accurate. Like on the edge of a p plus epi, it will be point 0.002 or something.
I see.
It's accurate. It should be the right one. And the second would be C computed from emergence of cross ratio. So eta is really a cross ratio in the following sense. So when we have a 4 point, we can define one cross ratio. But how about we have 1, 2, 3, 4, and 5? 5 point, how many cross ratios? Anyone can tell? Yeah, let's count. So at least we have those ones. One, A, B, and combine C and D. And then we can have a combine A and B, right? B, C, and D. And another one, A, combining B and C, and then D. So if eta is really a cross ratio, then consistency rule will be the following. We need to ask whether eta A, B, C, D, and whether the same and the product of the other two. Yeah, whether
It's
that's
like the pentagon creature.
oh
Someone seen it.
yeah. Some people told me about it, but maybe it's you last time. Was that you? Maybe last year. Okay. Yeah. So we can really check this numerically and identify whether there's any error. But we can derive it as well. So it derives from either the vector fixed point equation or stationarity. So we can really justify the emergence of conformal geometry. So if any some structureless conditions hold, that follows logically.
So this fixed point equation is really for a conformal theory, maybe not for. But I'll put it in a different way. Is this consistency condition enough to say that it's a complex structure? It is conformal, or whether it is just consistent with conformal, but not enough to say this it has a full conformal symmetry.
Yeah. That's a good question. I'll answer this after the short comment. Yeah.
Okay.
So in terms of C computed from here, this one is equal to C of the other one. Yeah. So the value of C is uniform. It's the same everywhere. So remember that axiom A1 is a kind of like a translation, like a emergence of a homogeneity. You can compute things from here. It's the same with computing from there. Like here we have the same conclusions, which is nice. But now let me answer Jenny's question. I think that's a super important question. Is that everything?
So you're saying that 3 can be proved from the fixed point equation, or 3 is a result of?
Yeah, the result from vector fixed point equation, or alternatively stationarity. Yeah, from there you can show that.
Oh, okay. I see.
Yeah. The answer is no. And the argument is the following. So the special C equal to 0 is a special case. Where we should have, we want A0 and A1. But I think those equations will become the version of A1. But we are missing A0. So it's missing.
Why are we expecting vanishing C implies A0 and A1?
Because the conformal fixed point, it's more general than the gapped fixed point. The gapped fixed point is a special case of conformal fixed point because it has more symmetry. It's topological. It's a conformal symmetry with zero central charge.
Okay, you're basically saying that topological things definitely have conformal symmetry because it doesn't care about even it only cares about topology. It doesn't even care about distance. Then conformal is definitely
Yeah, I agree, but this is not related to the value of C, right? This
but
is
C equals 0 corresponds to topological theory. No degrees of freedom. C is a counting of degrees of freedom. Entanglement entropy proportional to C. If C equals 0, that is right.
maybe we could discuss it later.
Yeah. Also, let me put it another way. I can also make some very strange, weird counterexample so that it satisfies the vector fixed point equation, but the two interval mutual information doesn't go to 0 when I shrink the interval size to 0. To small and small, it becomes a constant rather than go to 0 at the power law. So there are plenty of evidence. There should be another axiom, but we're still looking for that one.
Okay. But then you were saying that if you compute C and it is not 0, that it must be conformal.
Oh yeah, it must be conformal.
But is this relation equivalent to having the complete Virasoro symmetry?
No, not yet. I think that one is a little bit stronger, but may not be too much stronger. Yeah, we have a separate work on emergence of Virasoro, but that one we take some more assumptions and we test it numerically. It works
Yeah,
well.
I read that paper.
Okay.
So,
Yeah, but yeah, it's not sure. It's
I
just
see.
follow.
So it's
Yeah.
not it's not directly here.
Yeah, not here. But that's certainly one of the open problems on the to-do list. Yeah. How much time do I have? I think I already passed the time, so maybe I skip the Carol's intro. Or maybe let me just make one comment. Maybe someone. Yeah. So for the current central chart, you have some two-day system, a gap state. Current topological order ground state. And one important thing is that on the edge of the bulk, the physical intuition would be you can have some gravitational anomaly, that makes the left degree of freedom and the right moving degree of freedom different from the right moving degree of freedom. Sometimes you only have left movers. And this thing, this difference, C minus is defined in the so-called chiral central chart. It's defined by the difference. In the edge theory, this is defined by the difference between the left moving mode and the right moving mode. But but the anomaly should show up in the bulk. And the intuition is clear. That if the bulk is empty, then we always have zero chiral central charge. That there is a no-go theorem for lattice model. But now, if it's a non-trivial edge, it's a more left mover than the right mover, it must have something to do with the bulk. And so we propose some formula to compute the chiral central charge. The partition of the ball into A, B, and C, and then compute the modular commutator. A, B, C. I will three and the central charge. And yeah, there's a lot of comments. One is that actually there is a good theorem saying one of the we cannot simultaneously have auxiliary conditions below. Okay. And the first is the exact A1 with A1 in the bulk. Second is the modular commutator being non-zero. And the last one, the finite dimensional Hilbert space. Yeah. And at any finite length scale, we cannot simultaneously have one. If the Hilbert space dimension is finite, then we have exact axiom in one. So there must be some error. Otherwise, the chiral central charge should be exactly zero, so it should be
So
nothing.
finite HI is,
HI is the local Hilbert space.
oh,
Finite, I think the dimension of HI. Thank you. But yeah, I don't have the time to argue about this no-go theorem. But there is another interesting thing is that the gap the boundary, you can ask, oh, because we are doing entanglement bootstrap, we want to derive contradictions, right? We learn things by deriving contradictions. Can we learn the following? Can we say that the modular commutator is non-zero, and the gap of the boundary, maybe they are inconsistent. Right? For the gap of the boundary, we mean the boundary that satisfies the inversions of axiom A0, boundary inversion of A0, and boundary inversion of axiom A1. So for the boundary, if we have those two conditions, maybe that's inconsistent with the chiral non-zero chiral central charge. We do have such a theorem. The theorem says, because that's another no-go theorem, no-go part. That's if here is not, well, if the boundary is gap, then there is zero. Right. So this one is probably more robust. Well, I shouldn't say that way. It's like if we relax the error a little bit, I believe a version of the no-go theorem still exists, but this haven't been written down. That's something I need to think about. But the idea is that if there is non-zero, that indeed imply some non-trivialness of the boundary. But those are not everything. We still have an open problem. I want to end by writing down one last open problem here. So we have a definition of C. So this C is some and very important because the stationarity condition in terms of it, the numerical evidence really tells us this give you the correct one. But now let me call it the total central charge because this is intuitively the left mover plus right mover, everything is in that formula. It's summed up. But now we have the chiral central charge computed from the bulk, completed from the bulk to the function. So a very natural conjecture would be this chiral central charge must be less or equal to C total. So it's a really conjecture. Yeah, and I think it should be possible to prove this equation inequality under the framework of entanglement bootstrap, but no one have done it yet.
I don't believe the total is included in the ground state because there are counter examples.
What kind of counter examples?
Maybe I could briefly explain that. You know, there are different isolating theories.
Yeah.
Like C equals 1/2, 3/2, 5/2, and so on. And let me denote the numerator as the subscript. You could take value 1, 3, 5, and blah blah blah. And the fact is,
Okay.
so they are the same UFTC and therefore should be the same topological order, but they have different total charge.
Yeah, that's okay. So I haven't found the contradiction yet. So you say they have different central charge.
They have different left and right movers, but they are the same topological order.
Yeah, so the bulk are the same, so that's the same thing. I believe it's 0 in your case. So that the left hand side is 0.
Yeah.
Right hand side is
writing a
negative.
non-chiral topological order.
I mean, the right hand side is not even well defined in the case of topological order.
No, this is defined in terms of state. I'm not saying given a topological order we can write down C total. I'm saying given reference state satisfies this condition, then we can write it.
Then this definition will not be invariant under local unitary. It means in the same phase we can have different C total.
No, you're completely right. But now I'm not talking about the same phase or not. I'm talking about whether that's the same CFT fixed point. Yeah, CFT fixed point is more unstable than what you talk about.
I see.
Yeah.
So you're saying the CFT fixed point at the boundary always has a central charge that is bigger than the chiral central charge.
Yeah.
And if C minus is 0, that you can still have an unstable fixed point,
Yeah.
but then the CFT, the complexity of this CFT would be bounded. If the interior is very complicated, then the CFT would have at least this amount of central charge.
Yeah.
I think that's what you're saying.
Yeah.
It can be extremely complicated, a non-chiral, completely trivial bulk. You can still have very, very complicated CFT. But the complexity of the CFT, if I think of central charge as a measure of how complicated the CFT is, then the more complicated the bulk is, the more complicated the CFT has to be at the very least.
Yeah, that's the spirit. Yeah. Yeah, so this is follow from common sense, but it should be justified in the framework. And also, I'd like to let people vote. Like, do you think the chiral, like purely chiral CFT, like the chiral actually with only left mover, whether that one is more fundamental, or do you think the purely 1D CFT is more fundamental? What do you think? How many people think the purely 1D CFT are more fundamental? It has modular environment, it has the same number of left movers and right movers. Right? It's very nice. No one reads the
I think there is a counterexample that there are some CFTs with the same number of left and right movers that total, C minus is 0.
Yeah.
But it cannot be modular invariant.
Okay.
There is such counterexample.
Yeah, but that one is probably not realized by lattice model. Local Hamiltonian and lattice with tensor product Hilbert space.
I don't know.
Yeah, I think it's not, but we can discuss that. But you imagine, let me give you some evidence that I think the chiral version is more fundamental, or at least I give you some reasons to like this problem of chiral edges, because that's one of my favorite problems. So the argument is that this one is a stable fixed point. So if you add local perturbations, you cannot deform this state away from the fixed point. But that's a hard statement. Everyone seem to believe that it's hard to justify. But let me give you another version of the evolution. So take this system, you have pure state AB. And let's try to deform this state by the modular flow. It's like A to the power I times the real number S. I can state. The state evolves. And this is a very bad cut. So the state on A is the same, the state on B is the same, but the entanglement between A and B is changed. Yeah, including the part near the X. And naively, this drastic evolution of the state should break the conformal invariant completely. So the boundary will no longer be conformal. And if you test those conditions, stationarity vector fixed point equation near the endpoint, if the region contains the endpoint, it should be broken. But this is not true, at least as far as the numerical goes. It suggests all the evidence seems to suggest for purely chiral state. So if you only have left movers or only have right movers, those conditions are, yeah, it's super robust. The new state is also satisfy everything. It looks like a vacuum. Not so different from the vacuum, and it's only true for purely chiral state. So I'm very amazed by this fact. I feel like it implies that there's an ambiguity to determine which one is the true vacuum. So each one looks like the true vacuum. You can take that one as a vacuum.
You mean after evolving psi AB by the reduced density matrix of A?
Yeah. Reduced density matrix of psi on A.
Then you evolve psi with this row A.
Yeah, this is the unit
still satisfy the fixed point equation.
Yeah, so the new state, say S also satisfy the fixed point equation. So you have a non-trivial manifold of the vacuum-like state. So I feel like the manifold will teach us something, but we haven't
But
figured
then
this out.
would that create excitations in the bulk?
Yeah, that's right. That's right.
So as in, even if you create a few excitations in the bulk, the boundary will still be chiral and looks like it is at fixed point, something like that.
Yeah. So from the viewpoint of the original Hamiltonian, the bulk has excitations. And the state local density matrix does change. But the question is which one is the vacuum? So from the perspective of the new state, the original state sounds like an excited state. Maybe there's some relativistic point of view, like which one is better, we couldn't tell.
I see, this is quite amazing.
Thank you.
Because with the new state, you can also do some recreation and have a Hamiltonian.
Yeah.
Or then you might say that the new Hamiltonian and the whole old Hamiltonian can be related by finite depth circuits, local unitaries, maybe in the same phase.
They shouldn't be related by finite depth circuit.
Do you think they should not be related?
Yeah, there's a proof. Because the proof is the following. If you take an interval here and there, so the mutual information, let's call it x and y. So the mutual information of x and y computed from the state of S is sufficiently different. Yeah, it's different not by epsilon, but different by pretty large.
This is due to the presence of the chiral edge, this edge. If this is a gapped, everywhere gapped in the interior, then it probably is.
Then it's okay, yeah.
I see.
Yeah, those are functions of cross ratio. But even though the axioms are preserved, they have a different set of quantum cross ratio. reconstructed from the state. They evolve by some visible amount, so you can really distinguish them. But that's okay because we are talking about gapped states.
I see. So it would be a different CFT in some sense.
No, they should be the same.
The same, but then the notion of distance has changed. Central
Yeah.
charge the same, is that what you mean?
Yeah, central charge are the same, and everything should be the same. I believe so. But okay. But by the way, on this line, the axioms are okay. So the axioms are the approximate A0 and A1 are there. And then by finite time evolution. Yeah, so everything looks good, and we should conclude that they are the same phase. But there's no statement of saying if two CFT belong to the same criticality, they are related by finite depth circuit.
That's also true. But the bulk is, in some sense, still in the same phase.
Yeah, in a concrete phase, and I'll clarify that further in next Tuesday.
Good.
Yeah, there are a couple of things I was interested to cover, but didn't. One primary thing was so-called instantaneous flow. Or maybe let me take 3 minutes to cover it. So we have the modular commutator, which is a okay, so it's a scalar equation. And in the spirit of asking about the vector equation, operator equation, we can ask whether the vector, let's say vector version holds or not. If that, well, you first you can try this. KBC. That's an operator. Let's add this to the ground state. But I'm talking about to be completely clear. I was talking about the bulk topological order. The gap state can take the anyways A, B, and C. Yeah, to compute this one. Right. And the scalar equation I talked about was the KBC. It's pi over 3 and the pi central charge. And now let me remove the this is called brag and Cantor, and remove the brag. So it's become a vector. I'm going to ask whether this is proportional to the sum. It turns out the answer is no, it doesn't work. We tested this numerically. It's very bad, so it doesn't seem to hold at all. But it turns out we were able to find some correction terms. So in the original term plus we call it alpha A, B, C. We have to finite size error, so let me say this way. Oh, sorry. Current central charge pi over 3 simultaneous. Let me see. Where the correction terms are so the derivative of k. For the evolution on BC. IS. Yeah, so you have modular homotonic, you take derivative. Those are operators. We never think that
So for KBC, row BC or row AB?
you
KAB for row BC.
overrule BC because if you take AB, then the reduced density matrix is invariant, so you don't have any change.
Oh, I see,
Yeah.
I see.
Yeah, so this is AB. This is a different region.
I see.
Yeah, this is derived using the tool of instantaneous modular flow. Paper I'm finishing with 想你这样。Yeah, so this one is strictly stronger than the modular commutator. It seems to say something more about the density matrix. Hopefully, we can understand to get to hint to some deeper puzzles like the quantization of chiral central charge. We have no idea why the chiral central charge should be quantized on area velocity, but maybe this helps. We don't know yet. There's towards some future direction. Yeah, thank you. So I think that's all for today.
Okay, thank you very much. Questions online? Just